This morning, I guess I have to give two lectures, or rather, I guess we have to endure two separate lectures, but fortunately, they'll be putting Stefano Coraluppi in the middle, so that's good. It's always difficult to listen to 2 hours from the same speaker. I'm talking about tomographic multi-target tracking and its relationship to PhD filters. Tomographic is a very unusual word to mention in the context of multi-target tracking. And the reason for the word is because of some connections that I found between medical imaging, tomography, and the PhD filter, which really I was totally unaware of when I began. And so much so I wanted to find a nice phrase for it. So I went looking, and all journeys have secret destinations of which the traveler is unaware. Certainly when I began the study of the multi-target tracking problem, by this and by other methods actually, some years ago, I never expected to encounter tomography, totally unexpected. So that's wonderful. It's a wonderful thing to find these kinds of surprises. So there's the secret destination the PhD filter had for me, and I hope it will have for others who encounter it, between with positron emission tomography. There's a hidden corollary, which is quite curious. The traveler is sometimes unaware of the direction of travel, by which I mean that when I began to read a little bit more about the tomography, because I was interested in it because of the relationship that it had with tracking, I discovered a subject called single photon emission computed tomography, and that was the secret destination because that's a multi-camera system for imaging. And that had a direct connection with multi-sensor intensity, or PhD filtering. So first I went from the PhD to tomography, and then I went from tomography to another subject there, and then I came back. It's a nice mathematical method, except it was really a journey that was quite interesting. So 2 lectures, topics in the first lecture. Many people are not aware of Poisson point processes, or at least what they are and how simple they can be. So I'm going to give some background on that. Then I'm going to derive the single sensor multi-target intensity filter, or PhD filter. I will speak of the intensity filter. I will call it the I filter. The I filter because, well, there is the iPhone, and it's immensely popular, and so why not an I filter? I will later speak of an ILRT, an intensity likelihood ratio test. Why not? It's fun. Names should be fun, should they not? So I'm going to derive it by 2 methods, one by an intuitive counting method, and that will be close to what you understand about point processes and the PhD filter. And then I'm going to skip to imaging, to tomography. It won't sound like tracking initially at all. And derive the, I'm not going to derive, I'm going to at least expose the Shep-Vardy algorithm, which dates to 1984 for tomography. Well, the PET tomography anyway, and then just point out that it's identical to the Richardson-Lucy algorithm, which was 10 years before that. So the PhD filter, for those who like to think it's mysterious and new and modern, well, the application to tracking is. However, the mathematics of it is, by the point of view of modern world, almost ancient. It's 40 years old. It's not new in that way. There is no reason why you should not learn about the PhD filter. None at all, because it is widely accepted in other domains, so it should be accepted here. I'm going to end this first lecture with a movie to show you the value of particle filter approaches to the filter, and I'm not going to explain too much about it, just sort of hint that in fact there's utility here and convince you of that, I hope. Lecture 2, I'll talk about lecture 2 in a little bit. Before I continue, is everyone listening to the lecture in this room today? The reason I ask is because sometimes I do, in fact often, like to use this laser pointer, and I know people in the other room cannot see it. So I'm going to, okay, there's a few seats here. If they're in the other room, they can come. Okay, I think that PPPs, Poisson point processes, are really quite misunderstood models. I do not mean that they are neurotic and need to go to psychotherapy. I mean instead that they are sometimes confused with the Poisson distribution. The Poisson distribution, and they're often also thought to be homogeneous, which sounds rather dull. Well, they are not. Neither of these things are true. Poisson point processes are intrinsically multidimensional. They are also intrinsically are best, and they're at their very best when they're non-homogeneous. That's what happens with the tomography. You don't want a picture of your brain that looks constant. That's not a very good image of the brain. So these are they're very flexible models. I think they're easy to understand. I know they're widely useful in applications, and they're the main focus here. In the tomography application, that is both PET and SPECT, the PPPs are a very, very good match between the physics and the engineering practice and the sense of data. It's a remarkable match. It's practically perfect. It's classic. In the multi-sensor and multi-target tracking data fusion problem, the model fit is an approximation. It's less perfect. It's good, it has its value, but it's not the same. So, modulo that there is going to be an approximation, the fit is still excellent, I think. So, the Poisson distribution, as opposed to the point process. The Poisson distribution is a discrete random variable. I'll often call it N. It has a parameter in it called a rate. It's a number, lambda. It's bigger than or equal to 0. The probability that the random variable takes N outcomes is given by this expression here. Without explaining how that arises, you can certainly see that that is a probability mass function, probability density function. The difference in the language does not interest me very much. But you can see if you add over all N, and remember how to expand an exponential, you can see that this sum is indeed 1 if you sum over all N. So it really is a PDF. It's equally straightforward to show that the variance is equal to the mean, which is equal to the lambda. So the parameter is the mean rate. Remember, the parameter is also the variance. So if you estimate the parameter, then how much variability is there in the number? Well, it's equal to the rate. If you think there are 10 things there on average, then the variance is 100. So that's rather large. I mean, that is definitely a problem, and it shows up as a definite problem in the tracking applications. For N bigger than a relatively small number, it closely becomes approximated by Gaussian. Central limit theorem will prove that sort of thing for you. Intensity function. Well, the Poisson distribution had a point, that is one parameter, lambda. And now let's suppose that there's a Poisson distribution for every point x in, say, the plane. I say in any Euclidean space here, but conceptually when I'm lecturing, I like to think of like a plane, points in a plane, or a volume, or a time-space continuum. It does not really matter. They are that flexible. So for each point, so each infinitesimal in this volume, there's a Poisson distribution on the number of occurrences of something in that volume. So we're going to have an intensity, not an intensity as a scalar, but intensity as a function, one for each x in the space. Knowing lambda then, full lambda of x, the function, is the parameter of the Poisson point process. Notice I've gone from one Poisson distribution to an ensemble of a continuum of point distributions, and I'm going to call that the point process. And this function, lambda of x, therefore characterizes the entire point process. I'm going to suppose that for any bounded set R, this integral is finite. So why would I bother to make such a requirement? Well, the language is kind of necessary because if it's homogeneous, the usual homogeneous point process, suppose you have one per unit area, 1 point per unit area everywhere, then if you try to integrate over all the plane, you would get infinity. So, but on any bounded set, you're going to have a finite number, a random but finite number. So this is going to be, or turn out to be, the mean rate for the number of occurrences of points in any bounded region R. Very simple language then, the point process is non-homogeneous if lambda is not a constant. Big deal. That's very nice. Very simple. It is homogeneous if lambda is a constant. The most general kind of intensity function we'll be looking at is something that anyone in EE understands immediately. The intensity function will be an ordinary function, lambda subfunction, plus a train of delta functions with known weights w located at each of the points x of k. That's the most general form that we will encounter. It is not required that this function here be, that the function, the ordinary function, be continuous. It can have step discontinuities. It can be a lot of things. That's not a problem, but it cannot have these generalized functions, direct deltas, or higher, like derivatives of direct deltas. It cannot have those. In most tracking applications, the sum here, the delta functions will be absent. The only reason, okay, there are reasons to talk about it because of there's an auxiliary function, an auxiliary space that I will be using, but I'll get into that when it's time. So an orderly PPP is one that's just defined on the space. Does not have direct delta function. So when you look at this general function here and this sum over directs, it's gone. So that makes it orderly. If it is orderly, then the probability that 2 points in a given realization of the point process are the same is 0. If it's not, if there's a direct delta function in here, there is a probability that in fact you'll get the same realization with 2 points located at the points x of k. So, now I could go on and define things in very abstract ways. I know people do not like measure theory. I like it, but I don't like it as much as measure theorists do. And you don't really need it, because what they'll do is they'll define many lovely properties. They'll sound very Euclidean, very nice abstract things. Then they'll work through some theorems, and then they'll wind up in a place where they then define a simulation procedure, and then they say that the simulation procedure will generate equivalently, will generate a realization of the point process, and it's equivalent to the definition. So I did a very uncharacteristic thing. I remember that there was a time when I was under 30, and I didn't really want to see the theory until I had an understanding of how to generate things. So if they're really equivalent, then I can do the reverse. I can define the realization in an idealized simulation way. I can define the point process, rather, using the simulation, and then derive nice properties from the simulation. Why not? Yeah, that's equivalent, too. It's not the usual procedure, but it works, and it's very economical to attitudes and computers today. So I'm going to generate a realization from this point process on any bounded region R. I want to do this for any region R implicitly. So you specify the region, and this is the way you proceed to generate a realization. Any region, it only changes the region. It does not change this two-step procedure. So first you integrate, basically the first thing you do is you integrate lambda of x over the region R, and you get a number, just a number. That number defines this PDF, the probability mass function, or the Poisson distribution on the number of points we're going to get. So we draw a realization of this Poisson distribution with a mean rate equal to the average of the intensity function over the domain. So we sample it, and perhaps the mean rate is, in a particular region, is 100. So when you sample it, maybe you'll get 123. Another time you may get 180. And a third time you may get 87. So given that you have, say, 87 points in that realization, where will you put the points themselves? That's the next step. The second step then is to distribute the points, the 87 points, say, that you're going to distribute. You're going to distribute them over the region R according to this PDF, and you can see from this definition it clearly is a PDF. It's a PDF that is proportional to the intensity function restricted to the domain R. So these are IID samples given the number, and that's it. You have to recall one thing. When you do this simulation, you will be generating the points of the realization in an order. There is a first point that you gather, there's a second point up to the 87th point. But the order in which you gather them is not relevant to your process. So, if you remember that, that's fine. If you want to remember that within your simulation so they're order dependent, that's a different problem. And so, when I say they're independent and identically distributed, I mean that the outcome is a list. It's a list in which the points will not be repeated unless there are direct delta functions. So if you're sampling from a continuous PDF, you're not going to get the same point twice. I think we've all seen that. So that's it. That's the Poisson point process. So you should be able, in principle, to generate a sample from any point process I would specify over a domain in which I've told you what the intensity function is. I would say one thing, though, about this notation. Realizations are really consistent of two things: this integer n and the points that correspond to that number. And you notice that there's in that appears in two places. And there are those who would say that that's redundant. And I say, well, this just shows that there's some correlation. It doesn't matter. And it's very convenient then, because we can speak then of the probability of the points given in, and we can speak of n in a nice way too, independently of what the points are. If I were to remove n from this list and not make this an ordered pair, of which the second part is a set, then if I want to speak of the probability of n, I have a notational nightmare in which I have to talk about the points in the, some very strange things come out of that problem. Nonetheless, this notation it's not universal, but it is very, very useful, and I think it dates to Snyder when he was first doing his work on tomography, actually. So here's an example. Suppose the intensity function is proportional to a bivariate Gaussian. I say proportional because the proportionality constant matters. I want to scale it, in this case, by a constant, and in this case, that constant is 100. So it's 100 times a normal distribution. Except that I actually take a slice out of it. I take an isthmus, a straight. We have a straight here in Turkey. So we will have a straight here. And these are places where no points are allowed. So how would we, I've normalized everything, so it's the Gaussian minus this straight, all normalized so it integrates to 100. So on average, the number of points would be 100. A notch is what I also say. So if I do the sample in the way I've just described, in this particular case I wound up with 90 samples. Here they are. I'm not sure how well you can see them. But when I superimpose the contours of the intensity function on them, you can clearly see what is the notch. You can quite clearly see it, but only after I've imposed the intensity function. If I had just shown you these data points here, even with 90 samples, even with such a blatant, obvious feature that there's a notch in this intensity function, you could be forgiven for not noticing it immediately. But it is there. It becomes there after you know it. So detecting such features are difficult. And so how do you estimate the intensity function? You need lots of data. Now, the reason I stress this is because with tracking, you don't have lots of data. You never have lots of data. Tracking is a data-starved problem. So you're trying to estimate an intensity function from just a few data points. That's going to be very difficult. It's going to be an inverse problem. It's going to be very difficult to solve. The imaging problems stress these kinds of problems all the time because they want more, they want you to be in the imaging chamber longer. They want to give you more radioisotope, but they can't do that because they may cause problems that they're actually trying to cure. So it's a complicated little thing. But for tracking, we have a sensor, and we don't have a lot of measurements, and we're trying to go from a few measurements to a whole function. That's classic disaster. That it does work at all is amazing, actually, and unexpected. One last point here. I'm sure there are some very keen eyes here. You'll see that one little point. It looks like, oh, he lied. He lied. There is a point in that isthmus in the notch. No, it isn't. It's Mathematica and the visualization. When I plotted the contours here, it really is a steep gradient, and it reproduces a smooth roll-off. And when it does so, this point looks like it falls outside. It does not, I assure you. This example shows up in my book on Poisson point processes. Since we're talking about advertising, I might as well say it. It came out last year at Springer. And because I didn't want to have to explain that little detail, I did lie. I took that point and moved it up just a tiny little bit so the question would never come up. So at any rate, this is a perfectly okay example. Now we're going on to that's really all there is to know about the point processes that are not just the straightforward definitions. You can get a lot of it, if you think about it intuitively, you can get a lot of interesting things out of it. And I'll talk about them in the context of this application to tracking. So it's a joint detection and estimation problem. I think others have said that. There's no reason why I shouldn't say it too then. The two are interrelated tasks. You have to assign the sensor measurements to targets. Which target, if you have more than one. Decide that they're there, in that case. Or you can assign them to clutter. I love to say, mostly to be a little bit provocative and with a room full of Turks. Why not? It's part of my character. A little bit provocative because once you know the assignments, you solve the hard problem, the really hard problem, the NP complete, the computationally difficult problem. Now that makes it sound like what's left over is just estimation and that that's easy. I really don't mean that. But I'm just trying to get your attention that the assignment problem is the key problem. If you solve that, or if the oracle comes down and whispers the answer to your ear, then you're left with a human-sized problem of estimation, which is still not without its difficulties. MHT, the multi-hypothesis tracking, is widely accepted with point measurements to be, quote, the best model for radar and sonar. It's not the only model. With distributed targets, there are other issues, but with MHT methods, these are, with those kinds of models, problems rather, MHT is often thought to be the best, or the appropriate thing. Each hypothesis, for those who are used to hypothesis, meaning say target present, target absent, in MHT the hypothesis refers to one hypothesis is a partition of the whole data set over time into data that belongs to target 1, target 2, etc., clutter. A partition in the whole is one hypothesis. So you maintain, that's why you don't want a whole lot of hypotheses, because each one is a partition. It's breathtakingly complicated even to think about it, but to code it is just a nightmare. For those who like to code, I'm sorry, I think it's a nightmare. I don't like to code very much. I do, but I don't care for it. So I call it by a foul name, but for those who like it, it really is an interesting work. It truly is. But you can see the approximation coming out. If that really is the right way to pose the likelihood function, then you can see it's already gotten very big, too big, and there's too much going on. You have to prune the hypothesis list to a finite number, and in that case, you're suboptimal. You have an approximation with the best. So in the beginning and at the end, there will be approximation in this problem. So there's no reason not to consider non-standard approximations like the PhD or I-filter approximation. And that's the kind that is being considered here. And I think it has certain advantages. This is meant to be a simple example. How do you actually use the Poisson point process to model a target that is always there? PD is one target, no clutter. How do you model that problem? Well, you could say that, well, I have a bivariate intensity here. This is, say, a target that's stationary, like a buoy or a beacon, not moving. And it's always there. This is just the state model. This is not the measurement model. It's always somewhere in a particular location. And maybe it dances around like the end of a buoy chain or something. So you're going to model it this way. This C, if I integrate lambda over all of x and y here, I'll get 1 times C. I want one target, so C will be 1 here. So the intensity function is proportional to a PDF. I warn you now, and do not think of lambda as a PDF. It is not. It's merely proportional to 1. And the distinction, conceptually, is very important if you start working with these problems. So you work through then, and the realization then has to be, well, how many points do you get in the realization of a Poisson point process with a mean number of 1? Well, I had a movie here. I had a movie here a couple of years ago. I lost it a couple of years ago, too, and I have not bothered to regenerate it. I've apologized in each and every one of these lectures for not having this movie. This movie was supposed to begin with, be a sequence of 25 scans, 25 realizations of the target. And you notice that the very first scan in this movie had exactly 1 measurement. That is exactly 1 point in it. That was fine. That's exactly what your intuition says. If you have a target, it's all 1 target, it's always there. So how many points you should get in a realization? It should always be 1. No. That's the approximation. It is not what you get. The very next scan had no points. And the scan after that had none, and the scan after that had 4. And so I had 25 scans, and I did overplot all 25 scans, and if you count these up, you get 23, not 25. So there's something wrong. PD is 1, there's 1 target, and I have not the right number of points in every realization. I think so that you can ask, well, so how often do you get the right number of points in a realization? And the answer is like 1/3 of the time. That's not very good. That's terrible. If If the points of the realization are the states of your target, then this is a hideous, a terrible, a monster model. What's an approximation to pi? 5. You didn't say how good it had to be. So this is not a good model. There is, however, a saving grace. The points of the realization are not the states of the target. What instead is, I don't think that's the right interpretation. The right interpretation is that it is the ensemble average of the rate at which you will get a target in a particular point in space. So you take one realization. Well, that's one of the reasons that I showed this. Where did it go? There. This is when I superposed 25 scans. I had 23 points. Well, that's getting close to the right number on average. 25 scans, 23 points. How many points do I get on average? Close to 1. So it's the average phenomena that is the model and not the particular realization. So when you go through the math, you can ask, suppose I know that there are exactly n targets, there is no clutter, and you can ask what fraction of the time do you get exactly n points in your realization, and it's 1 over the square root of 2 pi n. It's not very, and it gets, so the problem doesn't get better as the number of targets goes up, it gets worse. So if you have 10 targets, you get about 1/8 of the time, just 1/8 of the time with 10 targets, you have 10 points in your realization. So that's not the right interpretation. The second one, the one I prefer, the one I think that works really well, is that the physical reality of the model attaches not to the concept of the realizations, but rather to the average rate at which occurrences occur, and over an ensemble of realizations. And that average number is parameterized by the intensity function, which is, the intensity function is where your intuition lies. That's fine. That's a good place for it to lie. It does not lie in the realizations that lay behind it. For those who have thermodynamics in their background, and I understand more and more, many engineers don't, that shocks all physicists, most mathematicians. But what happens in thermodynamics is, to get a model of the world that you see, you posit this phase space. There's an Avogadro number of particles, real particles this time, each with a position and momentum, and you put a distribution on it, and then you integrate out all the variables that you don't know. And that integrated state, that's the model of physical reality. It's very elaborate. It's very, very beautiful. It's 100 and so years old now. Boltzmann and Gibbs were the founders of the field, basically. And they speak of these particles as these microstates. So you integrate over the microstates. When you integrate over the microstates and take this ensemble average, that's physical reality. In this way, I would speak of micro-targets. The points of the realization are micro-targets, and the ensemble average is what we're after. Okay, you might not like that language. I accept that. But so I don't even need to use it. But the reason I work so hard with the language and try to convince you that that's not a bad way to think about the problem is so why do I work so hard, is that the PPP approximation finesses the data assignment problem. I don't talk about it very much. The assignment problem that is lingering here is not an assignment of measurement to target. Rather, I keep one aspect of that rule. In the PMHT, which has been spoken of, I kill that rule. Here I keep part of the rule. There's at most one measurement per target. That's all I say. That's all I say. I don't make any assignments. And in the end, with the methods that are used, the assignment problem is replaced by an imaging problem, and the imaging problem is an easier problem to solve by methods from tomography, it turns out. And the benefit is, with the imaging problem, is you don't get an exponential growth in computational load. To get directly to the tracking then, I'm going to augment the state space with S, which is typically, like I said, your usual target state space, position, velocity, or whatever you like, actually. I'm going to augment it with a state that I call phi, which denotes target absence. I think it's a very appropriate space in which to do or pose problems that are joint detection and tracking problems. It was first done by a man that I know of in tracking applications. named Kopak in 1986. I like to mention him because he died young and he was apparently an inspiring leader at Xerox PARC, which created so many of the things that have changed our world today. And his website's still up, which is amazing. He died 30 years ago, something like that. At any rate, so we keep phi. The state space then is going to be called S plus because I'm going to take S and just augment this hypothesis called phi. So an integral over S plus is just going to be defined as G, a function defined on such a space. You're going to evaluate G at phi and integrate it over the rest of it. And that's the definition. For those who don't like those definitions, I can make it more abstract, but I don't think that will work here. And it's not necessary either, frankly. So what does phi do for us? Well, let's talk about these measurement likelihood functions. We need P of z given any point in this augmented state space. So P of z given x is just the usual PDF of a data point conditioned on the target at a particular point x. P of z given phi is the probability that z doesn't belong to any point, any target. So that's natural. That's the probability of that z is clutter point, basically. That's the interpretation we place on it. We need a transition function. We're going to map, again, a transition function from S plus to S plus means I have to use all pairs of combinations. So psi of y given x, where y and x are both ordinary points in the state space, that's the usual transition function we have now. It's called target motion. It goes from x to y with some probability, and that's psi of y given x. Well, what's psi of y given phi? Well, that's the probability that the target was in phi, that it was absent, and suddenly it arrives at the location y. It's called target birth. So this augmented state space has given us an intrinsic model via the transition function of target birth. And it's all part of one thing. Target death, well, that would be phi, psi of phi given x. So it's at x, what's the probability it jumps into phi? That is, it jumps off a bridge and dies. That's psi of phi given x. And psi of phi given phi, that's a little more complicated. I like to describe it as just bad karma. It wasn't alive before, and it's not alive now. And it's actually not, it sounds like it's a bit of a conceptual problem. It's a little detail in the method that has to be worked, but it is not a problem. It actually is very fruitful. But it is there, and I pointed out so somebody else can't accuse you of using the psi given phi transition as a weird thing. Just say it's bad karma. Now, I'm going to talk about the PPP filter, or the I filter, or the PhD filter, in what I call 5 easy pieces. For those of you who are old enough, you'll remember a movie called 5 Easy Pieces. Great movie, for those who remember it. I've never gotten a smile yet out of anyone with that line, so I may change my name here. But you start with an intensity function at the previous time, k minus 1, whatever time that is. That's the current intensity for time t sub k minus 1. We're going to predict it forward. What are the key steps? We're going to predict it forward. That's fine, because in any Bayesian model, you have to predict your target motion forward. We're going to pass it through a probability of detection test. That splits it into two parts, those targets that are detected and those targets that aren't. Then they're going to talk about updating each half of these. These are independent processes. We're going to update the undetected point process, and we're going to update the detected point process. Now, when I update the detected target Poisson point process, the update is not Poisson. Oops. I just hit a barrier. I can't recurse and go outside my system. So that's where this gets projected onto a PPP as an approximation to the Bayes posterior. But once I've done that approximation, you see it becomes Poisson, and now I get to do something really, really hard. I just get to add them. That's easy. Oops. And that's it. That becomes, I should have stopped. That is now the updated target intensity function called fk/k, and now, of course, the destination is where we started, and we can recurse. So I want to talk about each of the steps, not with too much detail, maybe with too much detail for some, but it's not too much detail. The multi-target PPP, as I said, has this intensity function, f sub k minus 1 given k minus 1 of x, and x is on the augmented state space now. Target motion is this psi function. It's the probability. I don't make too many distinctions between probability and a likelihood of a transition. It's easy to fix this if I go to measure theory. Then I have a uniform language, all very simple. It's a nicety of language that's not really needed. So I'm going to call it a probability, and you'll assume the units are basically correct. So it's the probability that the target was at location X and it goes to location Y, whether X is phi or whether it's a location in the state space. And in the usual way of Markovian models, if I know the transition function psi, then I can involve it with my intensity function f, and that becomes the predicted intensity. It's that simple. It's not any different for this just because this is a target motion model that has an intensity function in it. So what's the intuition? There is a rate called f here. It's a rate, not a probability. It's a rate at which targets arrive at y, and then now you multiply by the probability it transitions to x. You gather this over all y's, and you wind up with an intensity x, and that's the rate at which they occur at x. It's like at every point y, you have a faucet with water coming in at a certain rate, and it branches and goes to a certain other location x according to this transition function. And you combine all the pipes. It's that hard. And then you write it down in the more traditional notation, and see, this is over s plus. Break out the part over phi, and this first term then becomes a target birth process. So target birth is part of this transition. It's part of it. One of Wolfgang's students, Mark Shakura, has implemented this kind of filter. So, I go out of my expected discussion there when I talk about that. So let me go ahead. So this is the predicted intensity, and it lives on the entire augmented state space. And when you have realizations, if you want to simulate realizations of the predicted process, you will have repeated occurrences of phi. That's okay, because it's not orderly on the phi part, but it is orderly on the non-phi part. So that takes care of the predicted multi-target process. Now the probability of target detection. Here is actually the more interesting part, mathematically interesting. I get to say something really provocative at the end. For those who haven't seen it anyway, it is provocative. I start with this predicted intensity function, fk / k minus 1, and I'm going to suppose that I have a PD, a probability of detecting the target at x, that I know. It depends on where I am. X, by the way, could be position and velocity, but varied velocity is the notion of aspect angle. Not all targets are equally detected based on aspect. So you can build aspect angle dependence into this PD of x problem. So if you have aspect dependence, somewhat build it into the PD function. So that's the probability of detecting a target that is at x. PD of phi is the probability that an absent target, actually, one that isn't there, actually generates a measurement. So some people will speak of phi as a clutter generator. I don't think the language matters, as long as you know what you're doing here. So then piece number 2, as I call it, is the target detection process. Remember, how do I deal with the model? It's a realization. I go through the points. So I have a bunch of points that are now one realization of my predicted process, and I check each point in turn. I toss a coin located at, say, x, and I decide to keep it with probability PDX, and I decide to throw it away with probability minus PDX, and that way I go through the list. I do this for any realization, and then I characterize the set of all realizations as its intensity function, and I wind up with 2 processes, one of those targets that I keep, and those with the targets that I don't keep, and these give you 2 different processes, those for detected targets and those for undetected targets. And you can easily see that this would be the intensity function of each. Here's the wonderful thing. Because of the realizations, the way I generated them, it looks like if I keep a target and add that to my detected target list, well, that same target, if it's not detected, would go into my undetected target list, and so it would seem that I have 2 highly correlated processes. If I have one, I know the other. It's not true. The detected and undetected target processes are actually independent. Completely independent, even though they come from the same source. There's a very convincing proof, very easy to write down, but for some reason I didn't want to write this particular equation, but I wanted to say it in words. Suppose I've got a coin, and I want to flip it 100 times, exactly. It's a fair coin, or not, as you wish. Just, you've got a coin, you're going to flip it 100 times, and so it comes out heads 55 times. How many tails did you have? 45. So what's the probability that those are independent? 0. They are not independent. If I have 55 heads, I have 45 tails, period. The difference is, what if the number of times I'm going to flip the coin is from a Poisson distribution with a mean of 100? So on average, I'm going to flip the coin 100 times, but the first time I walk up to the stage and flip the coin, well, first I have to figure out how many tiles I have. I know the mean is 100, so I go out in the hallway, say, and I said, oh, it's going to be 123 times I'm going to flip the coin. So come on stage, I'm going to flip the coin 123 times, record so many heads. How many tails do I have? You still have the numbers, and you can write them down. Now you look at this over, I go out in the hallway a lot. I'm a bad boy. I go out there a lot, and I come back, and each time I give you a number, set of heads and a tails, the list of heads and tails are not correlated at all. They're completely independent. That's the phenomenon, and it has to do with the fact that the number of trials is Poisson. Now that sounds like an academic argument, but I think probably somewhere in the last day and a half, you've heard of spooky action at a distance in the cardinalized PhD filter. If you do not make Poisson assumptions, you will have spooky action at a distance. No question. You must have it. And if you do have Poisson, you won't have it. Well, now, Martin Lomke, another colleague of Wolfgang's, says to me that there are ways to have spooky action at a distance even with Poisson. I'm not sure I agree with him, but I wanted to warn you that there are people who disagree with that statement. But if you don't have Poisson, you do have it, and that is for sure. And the reason has to do with this statement here. So cardinalized PhD filters, since they don't have a Poisson distributed number of outcomes, are spooky. That may not hurt you, by the way, as some Peter has probably said. It may not be a problem, but it is something you must think about and see if it's useful or important, rather, in your particular application. Okay, that takes care of the PD problem. Detected, undetected targets. Well, I needed to make you smile, and I also needed a space. If it's undetected, there's really no data, so you don't really update it at all. The intensity function is, the updated is the same as the predicted. And I needed a way of saying that and making you laugh. And for American baseball, there's a very, very remarkably pleasant man from the 50s named Yogi Berra who said the most insane things, stupidly obvious things, and they made you laugh. So you can observe a lot just by watching was one of his things. The game's not over till it's over is another one. It's an unending supply of such trivia, and he always made you laugh. So it's easy to update the undetected process. The detected target process, that's the more fun part for those who like math. Now, I'm not going to give you the Bayesian update because there's an intuitive update that's very compelling for those who like point processes. It's also it leads you immediately into ideas that are tomographic in its character. And I'm going to suppose that I have a bunch of measurements, M of them. They come from the same PDF, P of Z given X. I have this predicted process. So now I want to know, what is the probability that one of these measurements, let's say the jth one, what's the probability that the jth one originated, that's what I mean by this arrow here, that it originated from a target in X, in the infinitesimal X plus dx. That's actually a ratio, is it not? It's the probability of targets that come from the infinitesimal and generate a measurement, that particular measurement, from the infinitesimal, and targets that generate that measurement from the entire state space. That's fair. It's the rate at which you're getting that measurement from this particular part of state space, and that's a decent thing to do. So you write that as a ratio. It's the expected ratio of expectations. The numerator is P of Z. It's the integral. This is a Poisson process, so it's the integral over the infinitesimal. The integral over the infinitesimal is just dx. That's easy. And you just evaluate P of Z given x times the predicted density. The denominator is the integral over the entire state space of the same quantity. That's fine. So that's my best current estimate of how many, of the probability of a target in X generating a measurement. But now I invoke the at most one measurement per target rule. So if a target generates, so if under that model, then if I want to know the total number of measurements that could have generated that target, that measurement rather, the total number of targets that could have generated it, then I add these probabilities. Notice I didn't say that two targets couldn't have generated the same measurement, but there is, if they do generate it, they're different targets. There is at most one measurement per target rule. I still keep it, and I sum. So I wind up summing to get, let's see, where am I on the slide? I can see here, but I can't see over here. Yes, oh, now I see. It looks really different at this very oblique angle, I'm sorry. So you sum the probability, that's this probability here, you sum it over all the measurements, and that gives you the total number of targets the estimated number of targets in the infinitesimal that could have generated the measurement. So, okay, that's one. The other part that I need is the estimated, or the expected number of targets that are in the interval x plus dx. So one is the number of targets that generated the measurement, and the other is just the predicted number of targets. And that is going to be the integral, or again, over the infinitesimal of my prediction, and it looks like this. Okay, so I'm going to say that the information update is to set the expected number of targets equal to the estimated number of targets. Not quite. It's the estimated number of targets. Notice that's a number. I have to say the estimated number per state space, per unit state space, hence the division by dx. And so this part, this is the expected number of targets. So I've substituted that in here. Notice I have the dx there. And to get the other side, I have this sum with the dx here, going into this sum, going into here, and then the dx that here it's all the way down, that cancels. So the dx's go away. And you wind up with this kind of information update here. So the detected target update is the prediction times this sum over the data. We are actually almost done. This is an approximation because I set the expected number equal to the estimated number. That's an approximation. The character of the approximation would become clearer if I went through a Bayesian derivation, but this is very intuitive, especially if you can take some time later to think about each of the steps I just showed you. But with the approximation built into every step, I start with a PPP and I end up with a PPP, and the recursion is closed. So that's that. Now, the last part then is simply these processes I stressed before are independent. When we add or superimpose two independent processes, you add their intensities. And so when you add these two together, you get this. And so for those who are familiar with the PhD filter already, you can see it. It's right here. I got a little work on it a little bit more to make the PhD out of it. So I get an integral over the augmented state space. So I need to reduce it to the ordinary state space in order to get the PhD. I don't say much about it, but actually just the fact that it's over the augmented state space makes it possible to get online estimates of both the clutter measurement clutter densities and also the target birth densities, or I should say intensities. Like I said, I don't make much of it, but that's what's possible. So let me go back. So I take this denominator integral now, and I rewrite it, just expand it by what it means. I am getting fat finger here. Yes. Now, so, this isn't supposed to do that. Okay. So, let me try it one more time. Okay. So when I write the two parts of this integral over s plus as a leading constant term, this is the clutter intensity. It's a function of z, right? It makes sense. It's the rate at which I get clutter, that's f of phi. It's the rate of that times the rate at which it remains clutter, that's the PD of phi, times the probability that I actually have clutter there from my clutter model. So when I do this product, however, I have a clutter intensity that is not the one I started with. It's a modulated form of it, modulated by this predicted number and so on. But actually, it's a scale multiple of the clutter intensity. So the shape of it I don't estimate, but I will wind up estimating its overall intensity. And then the other part here is just the clutter, just the distribution of measurements that come from target. So in the equivalent form of this filter, it's written this way, where I take that denominator term and split it into two parts. And now how do I get to the PhD filter? It comes directly from this. That clutter term is what's going to be changed. So I'm going to limit the filter, that is, restrict this I filter to the state space S. We'll get rid of phi. In doing that, I'm not going to allow transitions into phi, so I need to thin it with a depth process in order to do that. So it's a separate process. I'm not going to have transitions out of phi. Remember, I'm killing off phi, so I can't allow transitions into or out of. I have to compensate for them in some other way. When I do that, I'm also going to replace the birth process, which came out of my Markovian model. I'm going to replace it with some a priori birth intensity, which I'm going to suppose that I know. I'm also going to take the clutter and replace it with an a priori clutter model. And when I do that, I can write the filter, and this is identically the PhD filter, without any variations. Now, the notion of substituting in quantities into the posterior that I know from other sources, that's not done much, but it is done in, like, the Schmidt-Calvin filter. It's also done in physics. I understand that renormalization methods do this sort of thing to prevent certain kinds of theoretical collapses. They're not happy about it. Nobody's happy about substituting into the posterior, because the posterior is supposed to put everything you know about the problem into the math first. Now, if you don't quite do that, then you have to do something. And so even the physicists have been reduced to it, to their great humiliation. However, in this case, there are approximations, so it's not so difficult. When you do these substitutions, too, you might actually regularize it, because you might have a better a priori knowledge of clutter and target birth than actually you could compute on the fly. Again, Marek Shikoro's paper suggests that that's not so. But now let's move to brains, a lot more colorful. And you'll see the connections now. So far, I've told you about the point processes and stuff. I've talked about tracking and how you get these filters. And now, to see the connection to the tomography, I have to tell you what tomography is. So let's forget about tracking for at least a moment. PET imaging is what I'm talking about. Positron emission tomography. The image that is going to be that you see in these PET images is an intensity function. There's a value of the intensity in each and every pixel of the image that you see. It's a Poisson point process, spatially distributed, and that's actually the image. They show you these things, and they call them pictures, but they never tell you what the name is. The name is it's an intensity function. There are at least 4 discoveries, all independent of the algorithm. The one that is most famous in tomography is Stefano. This is a beautiful, absolutely beautiful paper. I've been recommending it highly everywhere. It's a lovely discussion of the math. It's an even better discussion of the engineering. And it's a very, very good discussion of the physics, kind of paper that every one of us should write and read. Very few of us will ever do either of those. This is one of those papers, and I highly recommend it. It is very, very nice. Lang and Carson did a nice job, too, but this shows you the virtues, or lack thereof, of beam number 2. They independently discovered it as well, and they had their paper in review when Stefano's paper hit press. They pulled their paper out and added a few things, and it got published a couple of years later, but they are contemporary, so I add them for that reason. They were just a little bit off. These are both very good papers. But image deconvolution, Richardson did it in '72 and Lucy in 1974. Richardson was studying how to take noise out of dirty pictures, I think that some people call them. So you have speckles, say, in pictures. You want to declutter that. So he was looking at image recovery. Lucy was studying the heavens. He was looking at stars and trying to correct, I think, for aberrations in the telescopes. I'm not sure exactly what Lucy was doing, but Lucy was the astronomer, and Richardson was looking at dirty pictures. Maybe, not really. It was nice. I got the laugh I wanted, that's good. So I apologize for Richardson's memory. But in the image community, they don't speak of Shepard. They speak of Richardson Lucy. In the medical imaging world, they speak of Shep Vardy, and they don't mention Richards and Lucy. So apparently, in the tracking world, we're going to talk about PhD filters and eye filters, but we're not going to mention the others. I don't think that's fair. It's not even right. The one thing I would say, though, for imaging is that all fielded PET imaging systems, all of them are founded in Shep Vardy. These images have high resolution, and that means that they can be done. They are practical. They can have high fidelity. You'll base, in some cases, for some, hopefully none of your friends or family, but people will make life and death decisions on the basis of the quality, the resolution of these images. And they are Shep Vardy, and they are PhD filter. I submit that that's probably good enough for our problems if we put the same amount of energy into these methods that the medical community has done. Now, I say all of them. I can't say that. First, I'm not an expert in PET. Secondly, I certainly don't know all the proprietary algorithms out there. Those who do work in it will say these things, but they don't say that in print that I've seen. The reason is these algorithms are proprietary, and if you say company XYZ is using Shep Vardy, somebody's liable to say, well, you're using my algorithm, I want to sue you. So they don't say it except privately, but apparently they're all variants in some ways. How does it work? So you inject a short-lived radioisotope into the bloodstream, typically. You wait about 15 minutes. The radioisotope is attached to a sugar. Why a sugar? Because cells metabolize sugar. Gives you energy. When they metabolize a sugar molecule, the radioisotope is deposited in the cell. And so some cells have a higher metabolic rate than others, and those cells that do get more sugar, more radioisotope deposited. So and precancerous cells and cancerous cells are such cells, typically. Not all normal cells also have a variation in metabolic rate, so you have to find those that are in excess of the normal rates. So the medical problem isn't over just because we get this map for them. They still have a long way to go to make a decision of some sort. So we're just trying to help them, or this method is trying to help them find the spatial distribution of radioisotope, say in the brain. The radioisotope undergoes beta decay. Each decay emits a single positron. The positron encounters electron, and everywhere except in Italy, where they fall in love, they annihilate and they go apart in opposite directions. And when they go in opposite directions, you can detect this. How? With a bank of detectors that surround the patient. So detector A over here and B up here go off within a few nanoseconds of each other. So, and if it's the right kind of timing and the right kind of energy of the photon is detected, then you know that there was a positron-electron annihilation. Where? Somewhere along the cord. Where along the cord? You look at the time difference of arrivals, and that tells you where along the cord. So it's a physical process and a timing process. And so how accurately can they do this? Well, about the same kind of volume as my little finger here, about like that. So it's not so good, each individual one, but they get a lot of data. Lots of positrons decay, and lots of positrons are generated and annihilate. So this is called raw time of flight data. There's other data for those who like the medical problem. Turns out estimating time of flight data is very hard work. Here's the image of how it works. There's someone that we hope none of us ever have to know, lying surrounded by a ring of detectors. Actually, this is a small stubby cylinder of detectors. Everything you see on the outer edge is one ring. Back inside is another ring, and I believe there are supposedly detected here 4 rings of cylinders, 4 flat rings that have been stacked. This is cylindrical detection, so it gets quite complicated. You don't have to stay in the plane, but I want to speak that way here. So it's just like I said, the decay occurs, and these 2 detectors go off. That gives you the cord, and so on. There's a lot of good stuff in here because these are fairly weak. The photons have to go through a scintillation crystal, they go through a photomultiplier, and there's a position logic circuit behind it. And there's some serious engineering here. Let's not detract from that. It makes the math, frankly, I think the math is the easy part of this problem. The engineering is getting this right. Here's brain, not mine. I suppose it could be. I chose this image because for those who like images of distributed targets and poor resolution, maybe multistatic sonar, You could imagine, if you want to, that this is a distribution of target intensity, because there's a lot of ambiguity in where targets are in underwater sonar. So, at any rate, that's the kind of map you can get, and you can see there's some artifacts outside the brain. You can also see that there's fairly decent resolution, but it's not the resolution you'd like. This is actually now a 6-year-old picture. It can be made better. So how does it work? All I really want to do is convince you here of how the model does work. It's essentially a linear model. It sounds horribly nonlinear. All the nonlinearity in this problem is buried in the engineering that goes into the system. The image is broken up into a bank of these little pixels, like, by R sub K. There's K pixels. So notice it's going to be a two-dimensional image, but it's a vectorized image. So there's K pixels in the image. K is going to be on the order of 2,000-3,000, you hope. I mean, you want a good picture. And lambda is the intensity of the rate at which you detect, it's the intensity at which annihilation events occur in that cell. Now notice that's supposed to be proportional to the amount of radioisotope that's deposited in that cell. So in that case, we can write the intensity function then as a sum over the pixels of the step function, basically. So it's a bunch of little steps. And you just pick all these little steps and that's your image. So the data is here, and we want to estimate how many numbers? K numbers, these K lambdas. How many data? Well, we have M data. If M is smaller than K, do we have a prayer? No. We need a lot more data than M. And so now remember, I'm thinking of these as pixels, so I'm trying to estimate an intensity function from some data. And this data is on the order in the tracking problem of the data set you've got. You have a snowball's chance in hell of doing a really good job of this. So why it works is because you know so much about the physics in the tracking problem. So you work your way through here, and this is the likelihood function. Now, the only thing about this likelihood function is that it's nasty, but it's not that bad. It's an integral of a sum of things. Mu is the intensity function that we actually are observing. Mu is here, so it's a sum of, it's still linear, these constants still are here, but they're now fuzzed out with these blurring functions that actually are measurement likelihood functions. And so we have that, and it's a product next of this mu. Mu is a sum. So we want the maximum likelihood estimate. I said map here, it should be maximum likelihood since I don't have a prior in it. But this is the function we want to maximize, and we maximize it over lambda. Lambda is the vector of these little lambdas. Big lambda then is what? The image. And I'm running out of time. You can solve this, going right along. You can solve this in a couple of ways. You can solve the necessary conditions using your favorite maximum likelihood algorithm from MATLAB or anything else you'd like, or you can use EM. EM has certain advantages. It handles this product of sums really nicely. The iteration keeps the picture non-negative, that is, all the constraints are satisfied, and you can add other constraints as well. So the only thing I want to take from this slide, because Matthias will not let me say anything more about it, is the missing data in the sense of EM is all you need to know to make EM work and turn the crank. The missing data is you get a measurement and you need to know exactly the index of the pixel at which the decay occurs. That's the missing data. You put it into the problem and you just simply turn the EM crank. And when you do that, it's really just elaborate. It's like asking someone to differentiate something in calculus. There's formulas for it, there's a procedure, you just do it. And you write down the answer. And in this case, you wind up with a Q function, which looks like this. That's the auxiliary function. And so it's a sum, again, of these it's linear and lambda. We know the volume of each pixel. Everything in this red box is known to us, and there's a log. And I ask you to maximize this over lambda k. And immediately you notice I can estimate the intensity and pixel k independently of the pixels and all the others, along with all the other pixels, which is really very nice. So that's the iteration. Now let's go down to the small pixel limit. When you write this again, and you just take the small pixel limit and play a little math game, and you wind up with this as the small pixel limit. Can you see the PhD filter in it? you certainly can, because what I've left out is the 1 minus PD, but I can add it back. And so this is basically the PhD detected target update. I've left off PD as well, but I can put it in. So I want to show you a picture, to show you a movie rather, not just a picture, is to show you the value of it, because I built a lot. First I built up the theory, and then I built up the tomography, and I put a little bit of skepticism in it to make you think, gee, this could not possibly work. There's too much to estimate and too little data. So I want to show you a picture, not because the application is itself so compelling, but because you'll see that in fact it does work. In this case, it's a multi-static sonar data set generated by Pascal Detaille in the Netherlands. There are several source-receiver pairs in it, a monostatic sensor, and so forth. These things, again, Matthias will not let me speak of. Sorry, Matthias. I'm having fun with him because this is the last time I give this lecture in this forum, so it's permitted, I hope. The example actually was generated by 3 of my colleagues at Metron, Brian Osborne, Carol Orloff, and Rebecca Boswick. There's 5 tracks in all, points are estimated by a mean shift algorithm. If anybody does image analysis or point extraction from images, the mean shift algorithm has been around for 40 years also, by Fukunaga, mid-70s. It turns out recently shown to be an EM algorithm, equivalent to it. And it's a movie generated with a particle filter. In the next lecture, I'll talk a little bit about what particle filters are based on a question from the UK. I added a slide. 60,000 Monte Carlo particles here. For those who think that's too many, I say wait a few years. You'll wonder why you use so few. And this is the movie, and I don't think it works here. So let's see. And before I show the movie, basically I just want to, I'm going to show the movie. I think it works if I just go into it here. Can we have the lights down, maybe? Yeah, it's working. Well, there we go. 60,000 particles distributed all over the place. There's a target here. There's another very uncharacteristic target. This sinusoidally moving target was put into so people could benchmark their algorithms to see if they couldn't track this thing, then, well, if they couldn't see it, then they couldn't do the rest. There is going to be a target. There is a target here. I'm sorry it's a little blurry, but it's better on the screen. Let me play that one more time.
What about those straight lines?
The straight lines, some of those are sensors. The targets are moving and the sensors are... Yeah, the straight lines are the sensor pairs. One of them is monostatic. The targets are those in motion. There's one up here, there's one here, there's one that's going to show up down here. But if you focus in this area, there's nothing there, but you'll see that it's like staring at a dark part of the sky. Maybe there's something there, maybe there isn't. Flashes, nothing shows you, you're not sure, you stare. Well, measurements come and they go, and maybe there's tracks there, or maybe there isn't. So you get this instability that shows up. Now, the reason that I think that this instability is not more focused on is because it disappears over time. You get more data and you move on. So before the tomography aspects of this sensitivity to the inversion shows up, you move to another scan so you don't see it. So the tomographic problems disappear because of the motion. But you do see it by looking at one region where you know there's nothing, and you see this bubbling effervescence set of targets that come and go. Some of that is legitimate concatenation of data that looks like it might be a target, and some of it I think is something else. Let's see. Whoops, I didn't mean to do that. Or maybe I did. One more slide. Okay. So all I wanted to do is convince you really with this lecture that the PhD and the intensity filters are tomographic imaging filters. The image space is not a 2D image, it's the dimension of the target state space. So high definition 3D images, Hollywood can wait. This has higher dimensionality. There's a physical interpretation for the target model, which I think is very important. It really is, it's not spoken of outside of these kinds of applications. I've also tried to introduce, or I did introduce, the augmented state space as a very good way to proceed with these kinds of problems. Simon Godsell and a few others are now beginning to use this space. Even Ron Mahler has used it. Regularization, I've talked about the need for regularization. I haven't said anything much about it. I will say a little bit, I think, in the next slide. But I think the largest takeaway is the connection to tomography and this last line. There's now 39 years of experience in medical imaging, and is it really possible that all of that has no use whatever in the PhD filter? I don't think so. It's just a question of going there, finding what they know, and bringing it to us. We will stress it in our way with our problem, and hopefully we'll have something to say back to them, which would be really beating a sword into a plowshare, which is a very old-fashioned expression of saying taking a weapon of destruction and making it peaceful. So that would be a good thing, a charming thing, I think, for everyone to do. Are there any questions? No, okay, now are there any questions? Okay.
That would be great.
Only one.
Okay.
You have 10 minutes left, unfortunately, to deal with. Oh, Roy.
Are you serious? Yes. So let's see, the bad news is we have an hour before lunch.
No, 2 minutes.
We'll see. The good news is there are almost no equations in this presentation, so you can relax a little bit now after hearing Roy. So hopefully you'll remember a little bit of the, at least at a high level, some of the MHT's formalism that I talked about yesterday. But if you don't remember the details, don't worry about it. But hopefully you will at least remember that the MHT is I think it's not controversial to say that it's well, let me avoid saying it the most advanced or most sophisticated, but it's a well-established paradigm for target tracking. And I showed you yesterday some examples where, as we increase our hypothesis tree depth, tracking improves. And we sort of stop there, and I'm just going to show you very quickly a couple of examples where another reasonable thing happens, which is that as we increase the number of sensors, so here's an example from, does this go forward? Yesterday it was going, oh, I don't have this. Sorry, let me do this. Is it that simple, or do I need to do something? Let's see. No. Well, okay, I'll do it this way. It did work. Sorry. Okay, this is just an example to show you that if I take, this is from a sea trial, the details don't matter, but I have a target that's maneuvering, and we have some number of source-receiver pairs in the water, source-receiver waveform combination, and we get some tracks. And as we increase the amount of data going into the tracker, we increase the number of source-receiver waveform combinations, we increase the number of sensors. The image gets cleaner. We hold the tracker longer and we suppress clutter. So that's good. We're putting more data into the tracker of comparable quality, and less is coming out, and it's cleaner. It does work. It's just another example. This is the kind of thing that's nice in undersea surveillance studies, where we have targets that exhibit significant maneuvers, and we have a lot of contact data going into the multi-sensor, multi-hypothesis tracker, and that's getting reduced down to a fairly small number of objects, which includes the object of interest, which is critical, of course, and a well-localized track on the target of interest. And in fact, many of the other tracks are known fixed features. This is the Malta-Plateau between Sicily and Malta. And so there are some known wrecks, and there's an oil rig, and various things. So in fact, the number of truly false, spurious tracks is less than this. So this is the kind of performance that we can achieve. Now, just like yesterday, I showed you one example where if we don't do multi-hypothesis tracking, we lose the target when the situation is very challenging, and we only successfully track it when we increase our hypothesis tree depth sufficiently. There are also plenty of examples where monostatic sonar tracking is unable to track the target, bistatic sonar tracking is unable to track the target, and we can only successfully track the target when we feed the system monostatic data as well as bistatic data. Now this, it turns out, is an example with very high clutter rate coming into the tracker. And so the reason why the multi-sensor solution is successful is because, well, by having more systems, in this case 2 systems, providing scans of data to the tracker, our prediction time is, on average, twice what it would have been in the single sensor solution. So what does that mean? That means I have some uncertainty, track uncertainty, and rather than predicting a minute forward to the next ping time, I'm predicting, on average, 30 seconds forward. And as a result of that, my uncertainty ellipse, my track uncertainty ellipse, doesn't grow as much, so there aren't as many clutter returns that may lead me off track, and so I'm more successful in holding track on the target. You can also do some sort of back-of-the-envelope studies to convince yourself that multi-sensor systems will outperform single-sensor systems. So this is the kind of study that you can do where you consider, well, actually, let me go right to a later slide. Jump ahead a couple of slides. Okay, just to show you that if I have a source-receiver pair, now these are not signal excess plots. These are localization accuracy plots. So what does that mean? That means if I have a source and a receiver, and I have errors in timing and in bearing, then if a target is located close to the receiver, the impact of that angle uncertainty isn't so significant. But if the target is further away, the impact of that angular uncertainty, here we're plotting a scalar measure of error. So it's the trace of the measurement covariance matrix. And you can see that it grows as we move away from the receiver. It actually reaches this line of singularity as the target crosses the line separating the source and the receiver. And you can see that if we have another source-receiver pair, we have a different looking localization plot. And what's even more significant is the fact that for any given target location, if both systems detect the target and the detections are properly associated, then we have a significant reduction in uncertainty because of how the systems are distributed, and so the resulting fused localization looks as we see on the right. Now this is interesting, but very simplistic, because it assumes that both systems detect and that the detections are properly associated. So many times, many times we see multi-sensor tracking performance, like the examples I showed you previously, where we say, oh great, with multiple sensors, I do better. Or you have these back-of-the-envelope studies that claim the same. But the reality is, and this is really what I want to go into a little bit today, is the reality is that if we stop here, you might be convinced that multi-hypothesis tracking sounds good, and if I throw more sensors at the multi-hypothesis tracker, good things will happen. Well, the story is a little bit more complicated. So what I'm going to do is touch on a couple of items. One is I'm lumping it under what I'm calling cardinality tracking. So what I want to talk about limitations associated with MHT. One is a little bit more obscure, and I'll tell you more about it in a moment. And the other seeks to address the more obvious limitation with multi-hypothesis tracking, which is that we tend to generate a lot of hypotheses. We need to manage those. So just a bit on cardinality tracking first. So, and as a lead into this, let me just mention that, so yesterday I went through some of the MHT recursion equations, and they look nice, but the reality is that most people who do multi-hypothesis tracking, the theory is one thing, but when it comes to the implementation, they play some tricks. For example, when there's a scan of incoming data, the data is made available to the high confidence tracks first, and those tracks, in an optimal way, select measurements, and then what's left is made available to the less strong tracks, the tentative tracks, and those grab what they want, and what's left is made available for new track formation. So that's a trick or an approximation that doesn't actually match what the theory says you should do. The theory says that you should make those contacts available in the same manner to all your tracks and to new track formation. Well, but it turns out that empirically we observe that if we play these games, we do get better performance out of the tracker. So, and this, I'm just illustrating the fact that we've done benchmark studies of this sort with multiple non-maneuvering targets, or with single maneuvering targets, or with multiple maneuvering targets. And in all cases, and by the way, in these simulations, one of the concerns with making the data available to the good tracks first, one concern might be that, well, you'll keep tracks alive longer than you should when targets die. And in fact, that's not the case. So in these simulations, the targets die before the end of the scenario, and the tracks terminate. So these approximations turn out to lead to better tracking performance, and let's not worry about the numbers. But you might wonder, well, why is that the case? We see it empirically, but that's kind of annoying that we have the theory, and then we have to play these games to get better tracking performance.
Your mic is tap under your thighs. It's making noise.
Thank you. So the solution is to put it,
Stay behind up.
put it on your lapel. That's what I was saying. Thank you. Let's try that.
Okay, better. Is that better? Sorry about that.
Thank you.
Okay, so I don't want to spend too much time on the cardinality tracking problem, because I think it's a difficult thing to absorb in a few minutes. But let me just mention that a nice motivation for giving more weight to the good tracks can be achieved by looking at a limiting case of the tracking problem. In particular, the limiting case is the one where measurements give you no information about the target. So imagine that I tell you that there's no localization information, that there's no measurement space, but I simply tell you I see one object. Next scan I tell you I see two objects. Then I tell you I see 6, 4, and so forth. I only tell you the cardinality of the measurements. I don't tell you anything else. But your goal is still the same one. So with assumptions about birth rate and death rate and detection probability and the false alarm rate, you need to take the data and tell me how many targets there are and how long they live. Well, it turns out that, again, in this limiting case of no measurement information, save for cardinality information, and in the case in which detection probability is 1, it turns out that you can do optimal track extraction by arranging the measurements according to this tetra structure, drop all the measurements to the lowest row they can go to, and then extract tracks that are sufficiently long, where sufficiently long means that the contribution that I pick up from a track of length 3, say, provides some reward. It benefits me from a posterior probability perspective. And so you might extract the tracks as highlighted here. Now, in order to do batch extraction, I have to wait for all the data. Well, in practice, if I have a real-time MHT solution, I don't wait for all the data before I extract tracks. The data is revealed to me left to right. Well, it turns out that by weighing longer tracks more heavily, the right thing happens. So, provided you wait long enough, where long enough depends on the minimum track length of the things you want to extract, scan-based track extraction will achieve optimality. So at least in a limiting case, making those tweaks to, because the MHT theory it assumes batch track extraction. MHT practice doesn't involve batch track extraction. It involves some delay in data association, and some delay in real-time track extraction. The theory suggests that optimality is achieved by not just fully populating your hypothesis trees from the beginning of the data to the end, but doing batch extraction of tracks. We can't do batch extraction, and so we want to do real-time extraction, and provided that we weight things in certain ways, in the limiting case, we actually achieve optimality. Okay, that's, I think, as much as I want to say. Here's just an example of this, but the details don't matter, but I do want to say that one of the interesting things about this cardinality tracking problem is that measurements are extremely uninformative. And so, I wish I could go back a couple slides, but well, let me do this. It really changes the way you give a talk when you have these little delays. Let's see. Okay. Imagine that the false alarm rate for this problem. So again, I tell you I see one object, I see two, I see 6, and so forth. And assume that the false alarm rate is greater than 1. This is a fairly large area surveillance, and so I tell you I see 50 objects. Now I see 72. Now I see 12. So large area surveillance, and the false alarm rate, quite reasonably, is going to be larger than 1. Well, what's the optimal solution? So let's say that I form all data association hypotheses and I do optimal batch track extraction. Well, no track will contribute to my posterior probability. So the single likeliest solution is the null solution. Why is that? Well, it turns out to be the case because you don't pick up any benefit through measurements lining up well in space and time because there are no filter residuals in this problem. So the null solution turns out to be the optimal solution. But that's not good because, after all, these measurements are interchangeable. And so while a single sequence of ones, as shown here, may not score so well, I could replace this one with this other measurement, or with this other measurement, or with this other measurement. There are many identical solutions. So while one solution doesn't score as well as the null solution, a set of identical solutions taken as an aggregate group does outperform the null solution. And so I won't go into the details, but I'll just mention that we've worked through the MHT recursion, where rather than operating on single hypotheses, we operate on classes of global hypotheses, classes of indistinguishable global hypotheses. And if you do that, the recursion looks a little bit different, but it turns out that you pick up some factors which precisely match what the modified MHT does. You weigh the longer tracks more heavily. Now, you could address this cardinality tracking problem and say, you know what, this data association business, this is impossible. The measurements don't have any, they're not localized in space. It's extremely challenging. So you could forget about the cardinality tracker or further levels of aggregation, which I won't have time to discuss. You could attack the problem directly through a common filter and say, well, before I receive any data, I have a steady state expectation on how many targets there are and a steady state variance. And then, well, I can predict forward and say targets will die with some probability, and I expect there to be new targets entering the scene, and there's a corresponding covariance, and there's a common gain, and then there's a common update, which basically says, okay, I predict that there are some number of targets, and I know I'll see them with some PD, but I'll see some false alarms as well. And so I want to take the difference between what I see and what I expect to see. So there's the common update with the covariance update as well. The bottom line is this simple common filtering approach to cardinality tracking works very well. The truth, we have a common filtering solution, does very well. The MHT solution, the unique hypothesis MHT solution, as I mentioned for this problem, since the false alarm rate is bigger than 1, is going to be the null solution. The single likeliest explanation for this sequence of cardinalities is that there are no targets. However, if you introduce aggregation over indistinguishable solutions, the optimal class of solutions, class of identical solutions, looks like so. Well, that's a lot better than the MHT solution, but it's still not what you can achieve if you do further aggregation over very similar looking hypotheses, and it doesn't match the simple common filter solution either. So you might conclude, well, okay, you've gone through these 20 minutes and you've shown me an application of MHT or modifications thereof that doesn't even do as well as the common filter. Well, the nice thing about this is that if we now go back to the setting where we do have measurement information, this concept of identifying a class of global hypotheses, nearly indistinguishable. Actually, in this case, they're nearly indistinguishable. In the cardinality problem, they were indistinguishable. Here, they're no longer indistinguishable, but they're very similar. And the basic idea is, I don't want to find the best global hypothesis. I want to find a set of very similar-looking hypotheses that scores better than any other set of similar-looking hypotheses. And so, this is a slide that I showed you yesterday where, if you remember, I was talking about the two neighboring targets and the MHT solution introducing repulsion. Well, it turns out that if you introduce some swaps in measurements, any hypothesis that involves some swaps will not score as well as the optimal solution, but there will be many similar hypotheses. And so if you reason over that set of hypotheses, you can see that there will be an optimal number of swaps to be introduced as a function of target separation and uncertainty. And so that leads to the type of filtering result that I showed you yesterday with this equivalence class MHT. Just a final note on cardinality tracking. If you look at so I talked about this common filtering solution where we basically propagate means and variances. You could actually work out the full-blown posterior distribution. It looks very messy, but in the single scan case, it doesn't look messy. And let's just look at it in the case in which there are no false alarms. So this is sort of the simplest situation. I look. I expect there to be some number of targets before I look, as given by Poisson distribution with mean lambda t. So let's say I expect that there are 10 targets, but I don't know exactly how many there are. And now I look and I see targets with some probability PD or P. Okay, and so let's assume that I do that. I look with I think there are about 10 targets, and I look with, and I'll see them with probability 0.5. Assume, and I'll see some number of measurements. Let's say that I look and I see 7 objects, and now I ask you, well, how many targets do you think there are? There are no false alarms, so there are at least 7 targets if I look and I see 7. But how many more are there? Well, it turns out that the residual number of objects will be Poisson distributed with a smaller mean. So if the initial mean was 10 and I see them with a probability 0.5, and I'll say, okay, what's left? Well, I think they're about the Poisson number with mean 5. So this turns out is it's actually very closely related to what Roy was talking about earlier when he was talking about a 100 coin flips, Poisson number of coin flips though, not 100 deterministically 100, but some unknown number of coin flips, where the heads are the detections and the tails are the undetected objects, and so turns out to be the same. Now the problem is, if you wanted to do this recursively, is that now the number of targets is not Poisson, so this doesn't work nicely if there's a second and a third scan. So that's why the Kalman filtering approach to this problem is simple and effective. But the nice thing to note is that it points to the fact that in the target tracking community, we're very happy to keep things simple and to consider targets to be independent. In other contexts, that's not the case. For example, in the mine warfare community, undersea mine warfare detection problems, if you see a mine, if you detect a mine, that tells you something. It tells you that that's a region where somebody laid mines. And so the detection of a mine tells you something about the distribution of other mines. Targets aren't independent in that setting. Bringing that into a tracker will be very complicated. It's important to always question whatever assumptions you're using in your system. Okay, so the message here is that there's a very subtle suboptimality associated with the NHT, but also with other tracking approaches. It's not always the best thing to think of identifying the best looking solution. The more obvious limitation is the one I want to talk about now, which is the fact that there are limitations in computational limitations in MHD. Here's an example. It's another active sonar sea trial example. Again, this is the Malta Plateau. You see Sicily up here. And you see a lot of clutter. Well, it turns out that this is an area that NERC conducts a lot of sea trials in. And so with knowledge of the environment, so this is a result where we chose a standard waveform and used that in our things. And this is the tracking result that you get. Well, it turns out that if you optimize the parameters of the waveform, the bandwidth, the center frequency of the FM pulse, with knowledge of the bathymetry and the sound velocity profiles and all sorts of things that acousticians like, you get a much cleaner result. This is with running the same tracker with the same tracking parameters. Now, we're sort of cheating here, though, because we know the environment very well. What if we're going into an area that we don't know? One thing that you could do is to say, okay, I'll replace that broadband pulse with a number of sub-pulses. And so essentially I'll trade but I don't know which is the best sub-pulse because I don't know my environment. So I want to use all these sub-pulses. So basically the idea is trade your one sensor, your broadband signal, for n slightly degraded sensors because there's less energy in each subband than there was in the full pulse. Well, we found that it was very difficult to get good tracking results with this subband processing. And it was quite disappointing. If I ask you, give me your sensor, and I'll give you n sensors, and assume that they're as good as the one that you gave me, will you do better? Will your tracking solution improve? You would reasonably say, well, yeah, because I can always just ignore n-1 sensors. Surely I won't do worse. Well, it depends. All of these trackers that you're hearing about are suboptimal. And so if you provide more data into the system of comparable quality from an ever-increasing number of sensors, there's no guarantee that the tracker will do good things with it. So you can see this, and we find it experimentally, but you can also understand it by looking at a very simple performance model for tracking. So what does a tracker do? This is a simple Markov chain logical description of what a tracker does. The tracker starts in some initial state, and if you detect that, let's keep things simple and assume that one detection puts you into a tense track state. And then if you get enough detections in a window in time thereafter, you have a confirmed track. And now, as long as you don't miss the target, you'll stay in this good track state. If you don't see the target, you might go to a degraded track state. And if you keep not seeing the target, you'll eventually terminate the track. So you can look at the statistics that result from this process, and the track PD, so at the output of the tracker, track PD is the fraction of time that you have a confirmed track in the presence of a target. The track false alarm rate, well, that means that's how many times in the absence of a target a sequence of false alarms leads you to track confirmation. So we can look at output ROC curves synthetically generated based on this simple target model. So let's look at a set of these curves. So first of all, let's look at this single sensor ROC curve. Well, first of all, for those of you who know about ROC curves, you'll tell me that's not a ROC curve. ROC curves are monotonically increasing as the false alarm rate, or the PFA. Here we're talking about false track rates. But nonetheless, as I move to the right, my PD increases. If I lower my detection threshold on a sensor, false alarm rate increases, but PD increases as well. Well, things are different at the output of the tracker. If you keep lowering the detection threshold on your sensor, then initially you'll be feeding more detections to the tracker, and that's good. You'll do a better job of confirming track and maintaining track at the cost of an increasing false track rate. But you'll reach a point where if you continue to lower the detection threshold on your sensor, yeah, your sensor PD increases, but not in a significant way. And so you're adding a few more detections into the system, but you're continuing to increase the false alarm rate going into the tracker. That means that it's going to be more difficult to confirm track in the presence of a target, to confirm a true track in the presence of a target, and it'll be more difficult to keep that true track going. So the net result is that if you continue to lower the detection threshold at the input, at the sensor level, you'll keep adding more false tracks to the system, but with lower PD, track PD. The other interesting thing to note is that if you increase the number of sensors, you're putting data at a higher rate and driving this system, you don't get what you might hope to get, which is a ROC curve, a 10-sensor ROC curve that dominates the 1-sensor ROC curve, and a 100-sensor ROC curve that dominates the 10-sensor ROC curve. Rather, you get a family of curves, and in the end, you get a performance envelope. So the idea is, if you tell me the false track rate that you're willing to tolerate, I'll tell you, okay, that means I need to use 7 sensors and use a certain detection threshold across those sensors. If you tell me you're willing to have a higher false track rate, I'll say, okay, I'll bring in a few more sensors, and I'll lower the detection threshold across all sensors. Turns out that the best thing to do, by the way, is to match the detection threshold across all of these assumed to be identical sensors. Okay, so the message to take away from this is that there are limitations in performance in centralized tracking. Some of the obvious ones that we see when we process sea trial data are, well, first of all, registration errors. If I have 2 systems in the water and there's a compass error, say, or a timing error, my contact data, my dots on the screen, will not be aligned well. And so it turns out to be much more robust to give up on the idea of doing centralized tracking and let each system do its own tracking. Because after all, each system, if there's an orientation error, any one source-receiver pair doesn't care so much. The resulting tracks may be mislocalized in terms of their geolocation, but the track formation process will work. Turns out, I'm sort of approximating here things because in the bistatic case, an error in bearing actually does lead to an error in ranging. So there will be some distortion in the tracks. But roughly speaking, in the presence of biasing errors, if you let each system do its own contact-to-contact association, and downstream, by the way, when I say downstream, it's still real-time track fusion. It's not the batch fusion of tracks that generally people talk about in the tracking literature. It's a much more robust approach. Another effect that manifests itself in undersea surveillance is a fading effect, so that detection probability of 0.5 doesn't mean you're flipping a coin where you may or may not see the target. It turns out that seeing the target depends on where the source is, where the receiver is, where the target is, and how the target is oriented. So the detection data, if you look at a time series of zeros and ones, 0 when you don't detect and 1 when you detect, it's very streaky. It's not a random sequence of zeros and ones. And so that's a case also where it turns out that you'll do better if you exploit the streaks that every source receiver waveform system sees to form short duration tracks when that system is lucky enough to see the target. Because when that system sees the target, most of the other systems don't see the target. So if you try to track based on all the data, you'll kill the detection streaks. When Matthias is seeing the target, Wolfgang won't be seeing the target. And so if I interleave their data, I won't have nice detection streaks. And track confirmation will be difficult. Okay, so I would call those some robustness reasons why you might want to do distributed fusion. You could try to go for a centralized solution, but it's very difficult. For example, with the biasing error, generally speaking, you'll see work done where people perform cross-sensor data association, assuming that biasing errors have been minimized. Or they'll estimate the bias, assuming that the data association is known. Solving both problems simultaneously is very challenging. So there are robustness reasons why you would want to go for a distributed MHT or non-MHT tracking solution. But there are other reasons as well. And so let's think about the case where we don't have registration problems, and we don't have these fading effects that exhibit themselves in the undersea environment. Let's assume that the data doesn't have these annoying problems. Well, now can we say that we always want centralized tracking? After all, those of you who know about, say, filtering will know that people generally compare distributed estimation and filtering solutions to the best that you could do. The best that you can do is when all the data is co-located, no bandwidth problems, centralized filtering is best, right? Is the same true for tracking? Well, it turns out not to be the case, at least in the case, I'm focused here on MHT processing, and the reason why it's not the case is that even if the data is all co-located, I have all my dots from all the screens, from all the sensors, all on the same machine. If I run centralized MHT, that is a very particular way in which I will generate and maintain and prune tracks. It's not always the best way to generate, maintain, and prune tracks. There are cases in which doing multi-stage MHT leads to a much smarter way of managing your processing resources. So let me just step through some examples of this. So the first example, this is the one that Matthias showed you at the beginning of the day yesterday. This is very noisy HF radar data from an experimental German wearer radar that is being operated here off the coast of France. This is near Brest. And we're comparing, in order to know what's out there, we're looking at AIS data, which I talked about yesterday. So we're treating the AIS data as ground truth. So we want to perform tracking on all these black dots and compare the solution to the red lines. Well, it turns out we had a very difficult time coming up with a tracking solution for this problem. The data is very noisy. And the best that we could do involved a fairly simple multi-stage MHT approach that we call track, extract, track. And the basic idea is rather than coming up with
with an adaptive, more complicated MHT solution catered specifically to this problem, we thought, well, why not just use a common sense approach? Do some tracking where we're looking for the very strong tracks, and then take those out of the data. Meaning, take all the contacts that went into those tracks, take that out of the data, and look at what's left, and change your processing parameters so as to identify weaker targets, and take those tracks out of the data, and then look at what's left, and then pull those tracks out of the data. And it turns out that if you use this approach, you get tracking solutions that are still not great because the quality of the sensor data is poor, but you start to get some promising track extraction. And the interesting thing from a maritime surveillance perspective is that you also, this turns out to be a very strong track on an object in an area where AIS detection coverage is clearly good, and this vessel is not emitting AIS transponder data as it should be. This machine is getting tired as well. It's taking longer. Okay, so just another example of a multi-stage MHT. So here, imagine that I have a target or multiple targets in extremely heavy clutter. Well, I don't recall if Peter had time. Oh, he did talk a little bit about the MLPDA. So if you'll remember the MLPDA, this was an approach when the problem is extremely difficult, and there's too much clutter to hope to extract tracks on maneuvering targets. Just too many dots. So what do? You say, okay, I'm going to, there are different ways that you can think about it. One is you tune the process noise down to 0, or you assume a deterministic motion model. You're going to look for a low-pass filtering solution, essentially. You're saying, I'm just going to look for straight line targets. The rest, forget about it. It's too complicated to do the rest. That's what the MLPDA does. Well, you can do that, but actually do maneuvering target tracking as well by doing a concatenation of MHTs. Now, if I used a single MHT, I say, no, I really like my MHT. I'm going to grind through this data and look for maneuvering targets. You'll get solutions that look like these red tracks. You'll be pulled, you'll be seduced by false contacts, and it'll be a mess. Or you could take that motivation that the MLPDA provides, that use it in an MHT context, and the idea is to say, okay, I'm going to do MHT tracking, but with a very small process noise. I'm going to look for segments of track where the maneuvers are very slight. And in fact, if I don't see the target, I'll terminate track. I'm not going to try to associate detections across big time steps because there's too much clutter. And so coming out of the first stage, the first MHT stage, you'll have short duration, almost non-maneuvering track segments. Those segments can now go into a second stage MHT, where now I can increase the process noise, and I can allow tracks to stay alive even if I don't see them for much longer, because there's not much clutter to deal with at this point. I just have a lot of short segments. And in the second stage, I piece together these segments and form longer duration tracks. And so this is the kind of gain that you can get. Matthias, what time did I start? 20 to 1, was it?
Yes.
Okay. I'll believe you. Okay, so I talked about some robustness reasons why you'd want to go to distributed processing. And then I talked about some single target applications, because, okay, those were multi-target examples, but the targets weren't very close to each other. So those were really cases where the data didn't have fading and registration, but there was a lot of clutter and PD was low, and it were single target cases where you might want to go to distributed processing. But let's assume now that we don't have registration problems, and we don't have target fading effects, and the data is relatively clean. We don't have high clutter. Is it ever the case that it's still beneficial to do distributed MHT? Well, the answer is yes. When there are multiple targets in close proximity, when there's a lot of uncertainty about which measurement goes with which target, even when the data is very clean. And so there are a number of instances of this, and they're actually all very closely related. They have to do with persistent multi-target ambiguity. So the first case is one where you have multi-scale data, where I have something like a radar system giving me data on the order of seconds, let's say, scanning and seeing targets. But the detections are difficult to distinguish. They don't have much feature information. I don't know which is object A and which is object B. And at a much lower rate, I might have satellite imagery, which might tell me the dimensions of the objects. I'll see that one's large and the other's small. Or I might have signal emissions, or something that comes in at a much lower rate, but that is feature-rich. Now, if I take that sort of data and I put it through an MHT solution, what will happen? What's going to happen is that the high-rate data will completely swamp the system. You'll be creating a lot of hypothesis trees, and you won't have the benefit of reasoning over sufficient time step. You won't see the forest behind these trees. The first few rows of trees will kill you. So that's one instance that you can see, and I have an example in here which I don't have time to discuss, and so I'll leave it. It's in the slides, and you can try to look through it. But the interesting thing about this one is that this was a sea trial that we conducted in the Eastern Mediterranean in the fall of 2009 in cooperation with both the Hellenic and the Turkish navies, which turned out to be a very nice sea trial. Initially, we involved, by the way, both Greece and Turkey, because we were told, this was how it works within NATO, that, well, if you work with the Greeks, you got to work with the Turks. If you work with the Turks, you got to work with the Greeks. Work with both. Turned out to be very good because we got data from a number of different systems, and it was nobody laughed at that one, but it's actually true. Okay. This is an example, which again I won't describe, but basically you have the radar system swapping tracks. It gets confused and it can't figure out who goes where. But there's AIS data that tells you who goes where. The problem is the centralized solution doesn't work, and so the suboptimal solution, take the radar tracks and fuse them with the information-rich data. When there are swaps, we have to break tracks and start new tracks. You could go for another solution instead, which is track break fuse. I'd like to describe this very quickly to you. So, and in fact, I'll describe it in the context of the next example, which is actually, it's another instance of the same sort of thing. Two targets that cross very slowly. So it turns out that track break fuse is effective here. Well, what's going on? What's track break fuse? The idea is, imagine that I have two targets that are crossing very slowly, and if you remember yesterday I described this track repulsion effect that the MHT gives you. In other words, the target that's north always grabs the north measurement, and the track that's south always tracks the measurement of the south. And so, before the targets even cross, they start to repel. And so, even though we're running a tracker with a nearly constant velocity motion model, meaning we're looking for straight line motion, straight line subject to how much maneuvers we're willing to tolerate, but basically, the crossing solution should be likelier than the approach and repel solution. You would hope that your tracker, since it's looking for nearly straight line motion, would prefer the crossing solution to the non-crossing solution. Well, it turns out that that doesn't happen. This effect was first pointed out to me by Peter Willett, who said, you know, if the data rate increases, the repulsion effect gets worse. He was studying it with a hypothesis-oriented MHT when he decided to go ahead and implement it. And he suggested that we look at this problem. And my initial reaction to him was, well, Peter, you're wrong, because after all, if I increase my data rate, if I look more often, and if I'm looking for straight line motion, and I see that if I look more often, I'll do a better job of identifying the crossing. Well, it turns out that because of the track repulsion effect, things get worse as your data rate increases. You're even more likely to bounce, because you won't predict past the crossing. So how can we deal with this in an MHT setting? Well, the way we can deal with it is to reason over a lot of data. Reason over data that spans a significant time interval, and if you reason over all of that data, the crossing solution will emerge. Well, what's the problem with that? The problem with that is that here I'm showing you only the detections, but if you imagine having a lot of false returns as well, How big are your trees? If I have to wait for 10 or 12 scans of data, I have enormous hypothesis trees. I can't do it. I can't reason over 40 seconds worth of time. Well, the way that you can do the right thing with an MHT solution is to go, again, for multi-stage processing. Where, what do? Well, in the first stage, I treat the MHT as a filter of sorts. I want the MHT, or it doesn't have to be an MHT, it can be a GNN tracker, in fact. It needs to be a hard data association tracker, though, because what I want that first stage to do is to identify the good contacts. I know it's going to make a lot of mistakes. In a situation like this, it will not cross when it should, for example. But the benefit of that first stage of processing is that it removes all the contacts that you're not even seeing here anymore that I don't care about. It identifies the good contacts, but it associates them poorly. So at the output of that first stage, I will break all the association decisions and now provide this much smaller set of contacts to the second MHT stage. Now I can increase my hypothesis gate, my hypothesis depth, and look for the cross. And so what you'll find is that you can get comparable performance between centralized and track break track solutions, slightly different, but comparable. But the key is that the track break fuse or track break track solution will give you significant computational gains. Now, if in the second stage you do the same thing that you did in the first stage, you're adding computation with no benefit. But we care about, in this application, we care about going to deep hypothesis trees. And you can see that centralized processing can't achieve that. Okay, so we've talked about a couple of cases where even when the data is clean, the multi-sensor case, complementary multi-scale sensor, and slowly crossing targets, where multi-stage MHT provides performance benefits. I want to talk about, and this is probably the last one I'll have time to talk about, I want to talk about another instance in which multi-stage processing can give you performance benefits. This actually is not, strictly speaking, a multi-stage MHT, but it's, well, the basic idea is this. Assume that, I guess Roy showed he didn't show the Metron data set. Peter may have shown the Metron data set. At any rate, imagine an application where you have a lot of sensors, and they're very poor sensors. So they have very poor detection and localization characteristics. And just to keep things simple, assume that they're time synchronized. The more general problem would be a little bit more complicated, but let's not talk about that one. Assume that the sensors are synchronous, and they're looking at the same region, and they look at the same time. I have 100 sensors that look. Now, and then after a minute, they all look again. And after another minute, they all look. Well, what I could do is I could say, well, I like MHT tracking. I'm simply going to process one by one the data from 100 sensors, and then go forward a minute and process the contacts in step-by-step fashion. That turns out not to be a good idea, because you're forcing yourself to do recursive, real-time tracking, when in reality I have 100 scans of sensor data that are all identically timed. They're all coming in at the same time. Why do I need to limit myself to an MHT or any other scan-based tracking approach when that's a great opportunity to do batch fusion? Use a batch processing approach to collapse those 100 contact files into one good one, and then use the MHT or another approach if you prefer for what those are good at, which is to take you across time. So that's the idea between doing a first contact fusion step. And there are a lot of ways you can do it. You could, probably the simplest thing that you could do is to overlay in measurement space. That's what actually you're seeing results for here. Imagine overlaying in measurement space all the detections from those 100 sensors, and then gridding up space. And in any grid cell, if there are enough detections, you say, okay, there's a target there, and compute the corresponding fused contact for that grid cell. It turns out that it's simple and it works well when the targets are separated, but when the targets are close, it doesn't work very well. Because if targets are in the same grid cell, you'll declare target presence, but you'll actually have more than one target there. And so you might say, well, okay, I'll just make my gridding even finer so that I'll distinguish closely spaced objects. Well, that, remember, we're talking about poor sensors with poorly localized contacts. So the contacts from a target will be spread out over many grid cells. And so you'll dilute the presence of the target, and you may not see it at all because its contacts are in multiple grid cells. Well, you could try to work with the gridding approach, or you could actually go to a much more complex approach using the generalized likelihood ratio test. Or you could, and I'll just mention an approach that involves, again, we're overlaying the contact data, we're looking in measurement space, and we're looking at the likelihood function. And we could, as Peter mentioned yesterday, I believe, optimizing that, finding the peaks in that likelihood function is difficult. And we want to do something easier. So why not just evaluate that surface, this surface, at the contact locations where there's a measurement? And just evaluate it at those places, and then choose the good ones. Well, how many should we choose? Well, if there's some PD, and there's some expected number of targets, and there's some number of sensor scans, we probably want to choose, this is ad hoc, but you would want to choose a number of contacts that exceeds this rough estimate for how many good contacts you think there are. And then so this is a process to essentially clean up the data and then process the resulting contacts as you would have done, in our case, with an MHT solution, or with multiple MHT stages, as the case may be. And so that turned out to be, whoops, did I go backwards? No, I skipped over 2 slides. Sorry. In any case, that turned out to be a useful thing to do. So I'm going to finish just by mentioning something that it would be sort of the next logical extension to track before fuse and track break fuse, which is actually an in-between solution. And the basic idea is this. Imagine that I have a blue object and a red object. And now, unfortunately, they don't cross, or they don't just come together for a short amount of time and then separate. They come together, and they stay together for a lot of time. Okay? And I have radar data, say, all these black dots, and there are false returns as well. And I have another sensor which gives me feature-rich data, but unfortunately it doesn't report very often. So it might tell me, oh, I see the blue object and I see the red object, but then it doesn't report for a long time, and then a long time later it tells me, oh, I see the blue object again, I see the red object again. So now suddenly you know who went where. Well, if you do centralized tracking, what's going to happen? You're going to start tracking. You don't know what you're tracking, but you start tracking. Eventually you realize that you're tracking the blue object, and you keep going. And you do the same thing. You start tracking something, then you realize, oh, he's red, and you keep going. And very often you'll make mistakes when the objects are close. And then suddenly the feature-rich sensor tells you, aha, I see the blue target, I see the red target. Well, the simple approach that allows us not to do out-of-sequence state association and fixing errors back here, the simple approach is to say, okay, I detect that I made a mistake in my processing, I will terminate my fuse tracks, and I'll start fresh. So that would be the track before fuse solution. I'm sorry, that would be the centralized tracking solution. If you want to use track break fuse, that's what I described earlier. That means, okay, you form these tracks, then you break all the associations, and then you track through the data again, where now you only need to worry about the good dots, and you can do high depth MHT. The problem is that the targets stay together for sufficiently long, they stay together for n scans of data. You actually have a lot of hypotheses to contend with if you break all the associations at the output of the first stage. You 2 to the n on that order, hypotheses to contend with. And the fact is, you don't need to do that. When groups come together, it doesn't matter if you misassociate. What's critical, however, is that when groups divide, this is done for a 2-object group, but you can imagine it in a more general setting, what you really want to do is terminate tracks at the output of the first stage at key moments. In this case, when groups split. Start and then fuse these track segments in the second stage of processing. So in the second stage, you would now take fragments of track and piece them together. So this is sort of an in-between solution, this track segment fuse between the two extremes. And what we would expect, this is really conjecture, but what we would expect is that this sort of track segment fuse approach would have the performance complexity of track before fuse, but without those fragmentations that we see, for example, in the Eastern Med example that I didn't have time to talk through. But you would not have that fragmentation, but you would have the performance benefits of track break fuse without the complexity associated with track break fuse or with centralized tracking. So I think that I'm out of time, just about, and so good. I have conclusions. So hopefully, what I've said and what the other lecturers have said and will be saying later today have convinced you that, well, data fusion is important for a lot of surveillance problems in security, defense, and in fact in many other applications. Hopefully, I've convinced you that one good approach for multi-sensor data fusion is multi-hypothesis, and actually not only multi-hypothesis, but multi-stage multi-hypothesis tracking. The obvious challenge that we all know about in the MHT approach is hypothesis management, and multi-stage MHT turns out to be a simple way of doing sophisticated hypothesis management without trying to do it in a sophisticated centralized fashion. And there's a more subtle problem with the MHT, and in fact with a lot of other tracking approaches, which I addressed, where there are cases where we really should be identifying not unique, individually very well-performed global hypotheses, but classes of hypotheses that are nearly equivalent hypotheses that outperform the single optimal solution. And I'll just mention by, let's see, so I showed you a little bit of sort of hybrid ML-MHT. I think other areas that are sort of out there to be explored, well, Peter mentioned one, which is label-free tracking. One interesting idea might be to actually combining label-free with labeled tracking as a way of doing group tracking in a sense. So you do label tracking when things are easier, and when things come together, you would switch to label-free tracking and hopefully do a better job of doing things like localizing targets. And then you would switch back to labeled tracking when the targets pull apart. And the final point is that in the end, level 1 fusion, I think all of us who do level 1 fusion agree and understand that there are limitations with level 1 fusion, with detection level tracking and with track fusion. And there are surveillance problems. Wolfgang talked about these yesterday, where physical space, what I would call physical space reasoning is insufficient, and you really need to take the output of fusion engines and provide those to a higher level engine that tries to not just to track things, but figure out what's going on. That turns out to be, for example, in maritime surveillance, which is one of the big projects going on now at NERC, that's the really hard part. You can have a tracker that tells you where all the objects are, but if you realize that these are tracks, these aren't targets. There's no targeting involved. These are civilian objects. The hard part is figuring out what's anomalous in this civilian tracking. It's too hard for me, so I didn't talk about it at all. So I'll end there, and I guess we're ready for lunch. Any questions?